So now we are going to move on to the last talk of this session, where we see a familiar face again. We already gave the first talk. So let's welcome Alexandre again, but this time to talk about disentanglement.
Good. All right, so welcome again. My name is still Alexandre Moine. I'm still at NYU. This is collaboration with Stephanie Balzer and Alexandre from Carnegie Mellon and Sam Westrick and NYU. And so this paper is TypeDis, a type system for disentanglement. So disentanglement is a property of parallel programs, so let me set up the stage for parallelism. This is a small example. We have some data here. Wait, it doesn't matter. And then we allocate a reference on this data, CH, a channel, communication channel, and then in parallel we call F, J, and H, and name the result X, Y, and Z, and then do something with X, Y, and Z. And to summarize this program, we can draw what we call a computation graph that summarizes the parallel computation. Each vertex is either a sequential unit of computation or subgraph. And then two outgoing edges are a fork, and two ingoing edges are a join. So here we have F, J, and H. And disentanglement is a property of data accesses. So let's try to classify these memory accesses. For example, here, if we instantiate this H function by a size function that computes the size of the data inside the channel. There are two options when the write task loads or acquires the content of the channel. Either it contains all data allocated by some preceding task, and this precedence notion is important here. So we say that a task precedes another when the first task can reach the latter in the computation graph. So the data can be allocated by a preceding task or can come from a concurrently executing task. For example, it can be allocated by J or F. And disentanglement restricts what a task is allowed to acquire. So in particular, disentanglement says that a task may only acquire data allocated by some preceding task. So equivalently, we can say that a task may not acquire concurrently allocated data. The first remark we can do about disentanglement is that it's a property that broadly occurs. For example, pure programs are always disentangled, but also determinacy race-free programs are also always disentangled. But really the important part about disentanglement is that it enables task-level memory management. So the idea is that you can equip each task with its very own local heap that looks like a tree. And then because you have the guarantee that the tasks do not exchange location they allocated themselves, you have the guarantee there is no cross-pointer here between these heaps, so you can do parallel garbage collection without synchronization. So you can do parallel garbage collection very efficiently. And disentanglement is a property that is exploited by the Maple compiler that is developed at CMU, NYU, and RIT. It's a compiler for parallel ML, so standard ML with a par primitive. It takes two closures as argument, from unit to alpha and unit to beta, and return the immutable pair of the result of the closure after executing them in parallel. So the issue is that because Maple exploits disentanglement, it has to ensure that the program actually remains disentangled during execution. And Maple does that. It detects and manages entanglement at runtime. However, we are at POPL, so how to guarantee statically that a program remains disentangled? And we provided a first answer at POPL'24, where we proposed DisLog, a separation logic for disentanglement. However, as you may know, doing a full separation logic proof is costly, so here we try to simplify things and we propose a type system. So what is the intuition of this type system? Before showing you any rule, the idea is that because disentanglement forbids these cross pointers, it allows for two types of pointers. You have up pointers, so a task may point to a location located by some task may point to some other location allocated by a preceding task, or down pointers, a type from a parent to a child. And the very naive observation we make here is that for entanglement to occur, so for example, for this task here, to acquire some concurrently allocated data, for example, from this one, you need a communication channel between the two tasks. So you need a down pointer for entanglement to occur. So it means that if you only have a pointers, you're safe, and the program will remain disentangled. And this is exactly what the type system will enforce. We will force that every pointer goes up in this heap hierarchy. So the contribution of this work is TypeDis, a type system for disentanglement. The idea is that each type is going to be tagged with a timestamp, think of a region, and the timestamp identifies a task that allocated the underlying value. And the key idea of this type system, as I said, is the pointer invariant. A location may only point upward in the computation graph. We support several features, so polymorphism for both types and timestamps, subtiming, which is a cute name for subtyping for timestamps, and isorecursive types. And again, everything is mechanized, so in the log prover on top of the Iris framework. So what does a TypeDis type look like? First, we have unboxed type, TOW, which are totally standard because disentanglement care about things that are allocated on a heap. So if you have unallocated things like int or bool, no problem. Then we have two mutually recursive syntax. The syntax for boxed type, so things that are allocated on a heap, sigma, for a string, a ref, a product, or a sum, for example. And then general types, row, that are either an unboxed type TOW or a boxed type sigma annotated by some timestamp delta. And then, for example, we support type polymorphism. And the idea, as I said, is that newly allocated data will be tagged with the current timestamp. Here, if let's say it's delta 0, so if we have a string, hello, we have a string at delta 0, and if we allocate a string, a ref on a string, we get a ref on a string at delta 0 itself at delta 0. So we really have these identifiers everywhere in the types. Now, you might ask something, there is something missing in this figure. What about functions? So in our case, functions are allocated on the heap. They are boxed because they can be closures. We also, that's at the function type, we allow to universally quantify over timestamp. And crucially, function type is annotated by the timestamp of the task it will run on. So syntax looks like that. It extends the syntax of sigmas. And then for every timestamp delta, take a list of parameters row, and then here this superscript delta indicates that the function will run on delta. Let me show you some examples. So again, we have this string h, hello, and this r, a ref on world. If we have a function f that sets the content of r to be h, well, everything is all right, because h is a string at delta 0, r is a ref on a string at delta 0, so there is no constraint. You can execute this function at any task. However, if we have this function j that takes as parameter an integer I and sets r to be the string representation of I, then intoString will generate a new string, allocate a string, and because r contains a string at delta 0, we need this string to be itself at delta 0. So the whole function has to be called as at timestamp delta 0. All right, now the interesting part about par. So as we will see, the type of the primitive par is quite non-trivial. So I start by a very specialized type when we have two closures that will return an integer, an unboxed integer. So here this type universally quantifies over delta, the timestamp at which we are going to call par, and two irrelevant timestamps of two closures. And then par takes as argument two closures that have the same type. They say that for any timestamp delta prime, there should be functions that will be executed at delta prime and return hint. So this type really captures that the two closures will be called at some other unspecified task. So this type is admissible, but is really unsatisfying for three reasons. The first reason is what if the two closures return the boxed type? Also, what about type polymorphism? Can we have a polymorphic par? And also, is there a way to exploit the precedence information? Here, I forget that delta prime is a child of delta. And I'm going to answer all of these questions. So what about a box type? So this is a modification of the previous type, where the two closures return a ref of int allocated at delta prime. Now, what is the return type of par? Here, we would like to say, okay, give me a ref int at delta prime, but we have a scoping issue because delta prime is quantified here, and here we are outside of the quantification, so what should be the timestamp of the two return locations? And the intuition is that for disentanglement, everything allocated by a child will be accessible by the parent after the join point. So really, everything allocated at delta prime should be allocated, accessible by delta. And we take this intuition very literally. That is, we change the timestamp of the return location. Here, the type we give to par ref int is that par returns a pair of ref allocated at delta. So we forgot that this ref were allocated by some children. And at a very high level, that a good property to have is that you can hide that you used parallelism inside some function call and pretend that everything was allocated by the calling task. All right, now after about type polymorphism. So can we write a polymorphic par? Again, we can try. This is an admissible type in TypeDis. We can say, okay, give me two types, alpha 1, alpha 2. Give me two closures, going for returning an alpha 1 and alpha 2, and we will return a product of alpha 1 and alpha 2. It works, but it's very disappointing because now the two closures cannot return something they allocated. Again, it's a scoping issue. Alpha 1 is quantified before delta prime here, so alpha 1 cannot mention this delta prime. So we solve this issue with a sledgehammer, and we decide to go higher order. So now our types row can take timestamp arguments and can be applied to timestamp. So this means that types themselves have a type, it's called a kind, and a kind either a star, the base kind, or it's a function that waits for a timestamp and returns some kind. And now with that, we can write actually a polymorphic par, so that takes two types of kind, timestamp to star, and then we can require the two functions to give here a phi 1 of delta prime and then a phi 2 of delta prime, and in the return type, we just replace delta prime with delta. So we really replace every occurrence of the timestamp of the child by the timestamp of the parent. Okay, now if we try to take a step back, why is everything working? We have a typing judgment, which is simplified for now. We have a typing environment, gamma, the expression being verified E, the type rho, and the current timestamp delta. And really, in the proof, we need two key invariants. The first one is that locations in the context were allocated by some preceding task. For example, if in our context we have a x of type ref int at delta prime, and the current timestamp is delta, we know that delta prime is somewhere before us, so delta prime precedes delta. And then, as I said, we have this up pointer invariant, that's really the key invariant of the system, that says that if we have, for example, a ref on a ref of int at delta 1 itself at delta 2, we know that delta 1 precedes delta 2. We point upward in the computation graph. And when you combine these two invariants together, you know that every accessible location is safe for disentanglement. So, a small remark we can make is that so far the system is very rigid. Indeed, apart from par, there is no way of changing a timestamp in a type, and that really restricts you. For example, here, if we have again our friend h, hello, a string at delta 0, if we start a new task with a par and allocate a ref r here, that is, so with a new timestamp delta prime, so it's a ref on a string at delta prime itself at delta prime, and I try to write h inside r. Here I'm stuck, the type system will fail because I expect a string at delta prime, but I have a string at delta 0, no match, too bad. However, here it's perfectly fine to write h inside r because I preserve the up pointer invariant. So we relax everything, as long as, so the restriction of writing is unnecessary because we only need the two previous invariants to hold. So we relax everything and we introduce a logical graph to track these dependencies, and then subtiming, which is a subtyping that will allow to type check this example. So, logical graph, this is our way of tracking the dependency graph in the type system. So we mount the type system with context, delta, capital delta, and capital delta either empty or record a constraint that said that delta 1 precedes delta 2. And then the way to interact with this context is via a form of bounded quantification. That is, for each function, they can require some constraints to hold, so parameterized with this delta here, and at application time we will have to check that this constraint hold. And then we can add this information in par. So first of all, this is the final type of par. This is the most complex one. And it says here, like in the two closures that par takes, it says, okay, for any timestamp delta that I know delta prime, that I know will succeed delta, I will run on delta prime. So really, these two closures here now specify that they will be called at some subsequent timestamp. So now we have a time machine, and we can do what we call subtiming. So, for example, if I have a string at delta 1, and I know that delta 1 precedes delta 2, and delta 2 precedes delta, I can restamp my, my string and then get a string at delta 2. So, as you may know, subtiming plays dangerously with mutable state, and we have mutable references in the system. So in the paper, we have a general subtiming rule that allows for shallow subtiming, so subtiming only at the root of the type for mutable data types, but allow for deep subtiming for immutable data structures. Now, to show you a more complex example, this is par4. So par4 takes two bounds and a closure, and we call the closure to every integer between A and B, and does that in parallel. So it really simulates a parallel for loop. It will construct a computation graph that looks like that. And intuitively, for par4, we would like to give the following type. Give me two bound, timestamp delta, at which par4 will be called, and then a closure that will be called on some subsequent timestamp delta prime. And in order to verify this type, it's actually non-trivial. You need something called polymorphic recursion, because you can see here that the recursive call to par4 is made under a par, so we're going to call par4 with another timestamp. And you also need a way of changing a little bit the timestamp constraints here. So we really need some things, but we provide a way of, like, for polymorphic recursion and also subtiming this bounded codification. So we can give the following non-trivial type for par4. Now, the soundness. So this is a sound type system. If we are able to type E at type rho with some initial timestamp delta 0, then E is always safe and is always disentangled. The proof is conducted via logical relation in DisLog 2, an improved version of this separation logic DisLog. So to every syntactical type derivation, we give triple in DisLog 2. So this approach allows in particular for semantic typing. So if you have an expression that is not well syntactically typed, you can drop down to the program logic and actually give it a type. The main difficulties here were higher order types. Doing semantic typing doing logical relation for higher order types is quite tricky. But also, interestingly, that functions are boxed. So in our case, a function is not a value. And this is a big problem because it means that the value restriction, the way to have mutable state and polymorphism, does not work anymore. So we needed a way to relax the value restriction. And if you're curious about these questions, please come talk to me. As a conclusion, so I just presented TypeDis, the type system for disentanglement. The key ideas were timestamp in types, which must obey the up-pointer invariant. The features are type and timestamp polymorphism, subtiming, and isorecursive types. The soundness is conducted via logical relation, mechanized in Rock, Iris, and DisLog 2. And we have several case studies, so for pure algorithm. And the main case study is a deduplication algorithm with concurrent hashing. As future work, we would like to do type inference, so actually to have an algorithm generating types, and also to have existential timestamps to hide a little bit all of these timestamp binders in types. Thank you.
Thank you. So we have time for some questions. Yes, Julia. Can I just yell? No. You will get a mic by one of the student volunteers.
Thank you. Beautiful work. I really enjoyed the talk. Thank you. I'm just very curious. In 2002, there was a paper by Clark and Drosopoulou on disjointness of type and effects using ownership types in an object-oriented setting with a very similar idea that the idea of the ownership should go up and not down. I'm wondering if you're aware of this work, and if so, can you compare?
So I'm not aware, but here there is no ownership involved.
That's a name. So, but the idea to
but yeah, not aware of this
the topology
pointer
in upwards way that was there.
Yeah. Okay. I'm curious. I will look it up.
Okay. Thank you.
Any more questions? Okay, so you mechanized all this work in Rock and Iris. Did you notice, was there anything particular that you needed from Iris, or was it kind of like you do the usual approach of formalizing a logic and a logical relation in Iris, and then it all worked?
Yes, so it was the standard approach. No big modification, except for this value restriction. If you do semantic approach in Iris, you have almost bundled inside the logic that you need the value restriction. And as soon as you want to relax that, you really need to work hard.
Would you tell a bit about that?
Yeah, so I can tell it's just an issue of permuting the ghost update and the for all quantifier. You cannot do that in Iris, and we really need this similar rule for the value restriction.
So did you do the thing that has happened in some other works where you had a pure weakest precondition and you attack the typing judgment?
So sadly, I cannot do that because my functions are allocated, so they do an effect. And I did a very ugly trick I can share with you afterwards if you want.
And now I'm very curious about that. Okay, that sounds fun. Another thing is you want to do type inference.
Yes.
Do you have any idea whether whether type checking even is decidable in the system?
So type checking should be decidable. If you annotate everything, it should be decidable. And then for type inference, this really looks like a region type system, and there was a lot of work on region type inference. So we'd like to draw some inspiration from this line of work.
Okay, that would be a good idea. Yes,
hi, thanks for the talk. Could you go back to the slide with the rule for the parallel composition?
Yes. Here.
So is there some hidden relationship between delta 1 and delta 2 here, or can you really use any?
You really can use anything, yes. They do not matter because we are not, we know the type system gives you that delta 1 precedes the current timestamp, so you are allowed to call the function. We have very strong invariance in the type system.
I see. So you wouldn't be able to prove that it's type safe if you use some invalid thing where the return is coming before the inputs?
Yeah, no, it's not possible to do that.
Any last question before we are going to eat? Okay, I guess then let's thank all the speakers, and particularly let's thank them all for